I will begin with a word of prayer. Sorry it took me so long to get everything set up today. I'm not quite right. So anyway. Father, we thank you for this day, and thank you again for these students. Just ask you to bless this time we have and just help us to draw together the discussion we've had this semester and to prepare for the final, Lord. In your name I pray, Lord Jesus. Amen. So I have this participation exercise to hand back to you guys. It's kind of in alphabetical order, so I'll just start it here, and you know your name, so it should be fairly clear. I mean, it's mostly alphabetical order. I mean, there's some like minor aberrations from alphabetical order. So it's while we're waiting for that to get around and everything, let me just talk about string theory and supersymmetry just for a minute or two. So like last time I tried to explain to you guys that there's this thing called supersymmetry, which is a, hypothetical, currently unobserved, potential new symmetry of physics. And at the moment, I would say that its chief achievements have been mathematical. So like in the 1980s, Witten and others used supersymmetric field theory well, really to find new math. So in particular, there's another guy named Seiberg. So Seiberg and Witten invented these things that we call the Seiberg-Witten invariants. And you could calculate these things for particular physical models or spaces. I don't really know this stuff that well. I have a student who's gone on to grad school, and he starts to understand these things. Another one that's finishing his postdoc who knows these things deeply, actually. And so just to summarize what this is about, it's a way of using theoretical physics to calculate what's called topology. So what is topology? Well, topology, roughly speaking, is the study of the shape of space. It's a way of deciding whether two different spaces are the same. It's interested in questions like how many holes there are in space, or how many bubbles there are in space, or how many higher dimensional bubbles are there in space, and is it possible to take one space and morph it into another, things like this. So topology is the abstraction of calculus to the nth degree, all right? Like it's very new mathematics, the edge of it. And Edward Witten and Nathan Seiberg and others were successful in using instanton physics and supersymmetric field theory in a nutshell to calculate things in topology. So much so that Witten actually earned what's called the Fields Medal. I don't know if you guys know what the Fields Medal is or not. You know the Nobel Prize? Like the Nobel Prize in physics, it's like the big prize, right? There's no Nobel Prize in mathematics, but every 4 years, one or perhaps several promising mathematicians under the age of 40 are awarded the Fields Medal if they've done truly revolutionary work in mathematics. Witten was awarded a Fields Medal because of his work on these things. So Witten is, yes, Einstein's very impressive, but if you were to compare Einstein to Witten, I don't know. It's hard to, Witten's more of a mathematician, really. The work he's done he's essentially like the godfather of string theory. Just to give you a sense of like how epic Witten's work is, a typical really good physicist might have 500 citations to his work. When I left grad school 20 years ago, Witten already had 30,000. citations. And so he's kind of like the Pope of physics or something. I don't know. But then, of course, the Pope has its detractors, right? And there's a growing chorus of string theory is not physical. And those people aren't wrong, you know, because string theory isn't currently physical. So what's string theory? Well, string theory is in the early 1970s, and somewhat independent from this story, people were trying to understand the quarks that I told you guys about, I think, maybe more last semester. And to try to understand that, so one of the things about quarks is they're confined. Like you can't observe quarks in nature because they got fractional charge. So one of the things you might do to keep them from getting out and loose is you might attach them with like strings. There's these little strings attaching the quarks. And through studying this sort of string model for quarks, they just started studying like the quantum mechanics of strings, which is basically just like little loops that instead of having a particle, you have a loop. And how do you do the quantum mechanics of that? Well, you study something called the Virasoro algebra. And it's got really weird properties start popping out. Like, you know, it turns out like the bosonic string theory, it's only quantum mechanically consistent. There's something called an anomaly that cancels if you're in 26 dimensions. So that's kind of weird. And then, of course, there's more than bosons, there's also fermions, so they had to up the level of the string theory, add supersymmetry to it. They started looking at supersymmetric string theory. And it turns out, for reasons that are technical, you end up having to have your theory be 10-dimensional, 10 spatial dimensions, right? Well, how many spatial dimensions do you guys see? 3, right? So how do you have 10 spatial dimensions? So what do you got to do with the other dimensions? Either got to make them really, really big or really, really small. As far as I know, I've heard some theoretical physicists who know far more than I ever will say things along the lines of, I don't understand really large dimensions, I'm scared of that idea, which is a little bit disconcerting for a person who's done nothing but theoretical physics their whole life. But yeah.
Do they suspect illegal substance use in the derivation of these theories?
Do they were they high? I don't know. I did have a fellow student, not in my class, but the class above, who dropped acid to do a standard test in physics.
Did it work?
It did. He got a perfect score. Yeah. Sorry. Sometimes the government lies to you. Like, there is a beautiful side to evil. It's true. It's true. But but don't do drugs. For my final, no drugs. So anyway. So what people typically did with these extra, so you have, you know, so you had 10-dimensional space-time, which, if you're counting, I guess means we've got like 5 extra spatial dimensions. So what do you do with those? You got 6 extra dimensions anyway. So what you do is you wrap them up in some kind of small space. And so this is, you know, basically that's the idea, is like the extra dimensions, they're really small, so you can't explore them because we're big, you know, kind of like, and there's all kinds of analogies you can give. I read a book that was written in 1988 by Mikio Kaku, who you've seen on any number of science news shows if you watch. He's a Japanese physicist. I think he works at CUNY, and he has opinions on everything, so he's great for science news journalists. Like, you can just put him on, he'll say crazy stuff, it's awesome. He's a very interesting guy. But he wrote this book called Hyperspace, which explores higher dimensions and supersymmetry, string theory. I read that when I was, I don't know, about your age. And I was like, wow, this is really cool. And so I got interested in it, and then I pursued, you know, learning more in grad school and such. But, so where was I? So the... So you have this extra dimensions, and so these string theories I'm talking about, they were discovered in like 1970 to 1980, and the hope was that they were just going to be a self-sustaining theory of physics that would just explain everything. And basically the idea is, by, you know, choosing these little spaces that are hidden from us in the extra dimensions, you can give a shape to those spaces so that the way the strings wrap around them, it produces current physics. And indeed, people have been successful in producing theories of strings so-called branes. So that's the next step, is past the string theory. You start having to look at higher dimensional things, not just strings, but so-called branes and p-branes, and there's d-branes. Yes, there must be drugs involved, I agree. But anyway, that so-called superstring revolution, this so-called M theory, that was like late 80s. At that point, they realized that there wasn't just one string theory. There were like 5 different string theories. They're all dual to each other and part of one central theory called M theory. At that point, they left 10 dimensions to start talking about 11 dimensions with a 10-dimensional supergravity as a limit. Anyway, so, I lose track of the story about there because that's when I left grad school. But I'm pretty sure ever since I left grad school, string theory has been reinventing itself about every 3 years. It just keeps gobbling in all the rest of physics and making it its own. At this point, it's very, very expansive, what it is. But it still hasn't really done physics. Like, it doesn't make predictions. It's more of a theory of theories. So, but you should know, I think everybody should be aware that that is where the cutting edge of mathematics and physics is right now. A lot of the leading theorists and things are working on that. And there are other critics who say, well, it's a waste of time and it's not producing experimentally testable things, and those people are also not wrong. It has had some merit in like explaining the thermodynamics of black holes. So counting states of quantum mechanics around black holes, things like that. And it's also allowed us to have some insight into making what are called non-perturbative calculations in nuclear physics. So that is a much less esoteric thing than the string theory itself. So it's like not like the totality of string theory hasn't produced useful mathematics and useful new physics, and certainly insight into theory. It's very, very ambitious what string theory is, because basically what's happened is previous areas of science history, we've gone from like electron volts to megavolts, like maybe 10 or like 3 orders of magnitude from what we knew to the next thing, right? Like chemistry to nuclear physics to some of the things I was talking to you guys about, like the fancy excited states of neutrons and protons. Anyway, string theory jumps past that, like, I don't know, 14 orders, 20 orders of magnitude, something like this. So like, it is somewhat ridiculous to hope that we can get from, basically where we are to, if the stories are typically, if the story repeats itself as it has before, that's like something like 6 or 7, at least, I don't know, 5, 6, 7 revolutions in physics past where we are is where string theory is. It seems more likely that what we'll end up finding is something that's maybe 3 or 4 orders of magnitude past the physics we currently understand, not 10 or 20. But string theory is very, I guess the word seductive, perhaps. I was going to grad school, and the head of physics at NC State, he asked me, "You're going to grad school, what do you want to study?" And I was like, I want to study string theory. And he's like, no, we've lost another to the siren song of string theory, is what he said. He's not wrong, but anyway. And the reason I like it, it's pretty simple. It's math. I like math, and that's what string theory is. So it sucked me into it. So anyway, that's all I got to say about that. So I'll shut up about it. Give me a second here. I'll get the solution to the participation thing out. I don't have it posted yet, but I'll try to post this after business is done today. So not much to say here. Pretty much your final is, yeah.
Sorry guys, well, how many points is this out of?
25.
25?
Yeah. But there's more. So like if you were here the Friday before break, I gave you 20 points actually. If you weren't here the Friday before break, I gave you 25 points. But I also gave the people who were here Friday before break 25 points. So perhaps a more accurate way of saying it is I gave people who were here Friday before break 45 points for free. Well, and being here. And then I gave everybody 25 points. Because there's a participation grade, which I think I was going to give you guys quizzes this semester. I think that's what that was supposed to be, and I forgot somehow along the way. So it's just turned into me giving you points for the most part, except for this one thing I've collected from you and judged you harshly by your lack of sign or something. So like some of you are missing a minus. I took 5 points for that minus. I don't usually take 5 points off for a minus, but this is a significant minus. So, you know. Anyway, your participation grade can be as much as 70 points or as little as 25 points, right? So, but yeah. Does that answer your question? I mean, most of the thing I handed you back 25 points. So I'm sorry I forgot to give you guys more quizzes this semester. You'll forgive me, I guess, but
I think we will.
you will. All right. So here, so the thing is, if I look at this formula and I study the equation, this means that it's traveling in the positive y direction as time goes on. If I made that a plus, it would mean it's in the negative y direction. But it's not a plus, it's a minus. So this goes in the positive y direction. And so that means the pointing vector is going in that direction. It's parallel to y. But I know that the, whatchamacallit here, the electric field is waving also in the z-hat direction. So I need something like, you know, I need the cross product of E and something to give me y-hat. So what is that something? Well, z-hat cross x-hat is y-hat. So that forces me to put the magnetic field in the x-hat direction, which is what I did. And then the rest of it is the electric field magnitude is the speed of light times the magnitude of the magnetic field, which gives me this formula. And I was not super critical of what number or how you wrote this, so you might be wrong and still not have points taken off. But I was very, very... if I saw a minus, I tried to take 5 points away from you. So there you go. And then E cross B ends up being that. So, and I just decided to get to the point, the heart of the matter, which is to point out that the pointing vector, the units of it are watts per meter squared. How that actually gels out from the you know, cancellation of units for the electric and magnetic field, somewhat complicated. But yeah. Oh. Now, problem 2. So what I wanted to say is these are pretty much the 2 new problems that could be on the final that weren't on test 1, 2, or 3. All right? Of course, other problems that could be on the final that weren't on test 1, 2, or 3 would be like stuff we did in class but I didn't test on, but we spent a lot of time talking about. Stuff like that could appear on the final. So here, the main, most significant mistake I need to correct is some of you put 34 degrees for the angle here, but that's not how it works. It's the angle off the normal. So we got to go 56 degrees. So I think that's the main mistake about 4 or 5 people in here made. And that's the standard mistake. It's a time-honored mistake to make here, so it's a good mistake to make. It's got a lot of tradition and history behind it. So anyway, so that's pretty much it. You just, Snell's law, solve for the angle you don't know, and there you have it. There is, of course, much more to teach you guys about optics. I'm sorry I haven't done more of it. There's always more optics to cover, right? Like, you could do a whole course in optics, really. I think you did some more in the lab, though, right? Like, you got to do the lenses and the geometric optics stuff. 3 labs? Yeah. I hate teaching those labs. I hate them. I hate them with a pure hatred. Because there's like some places where you got to draw stuff off the page. It's like, what? Like, it doesn't fit, you know? And I always forget where it is, you know? It's so annoying. So you guys have any questions about the final? Let's see here.
Our highest test score replace the final.
I will not just replace your highest test score. Wait a minute. No! That is not how it works, sir. Nice try.
Jedi tricks are unique.
Yes. Yes, your Jedi tricks won't work on me. Nice try. I need you to take the final. I need a metric by with which to judge. Let's see here. All right, so you remember test 1?
No.
Here it is. You're gonna take a walk down memory lane here for a second. Oh man, I didn't move the thing over to the thing. Sorry, people at home. My apologies. The solution to the thing we looked at will be posted on Canvas sometime soonish. So to start with, we had a plain old magnitude of the electric force between two electrons. It's just the Coulomb force, just straight that. I think as you guys look back on this problem, and if you see that you got it wrong, after everything else we've done, coming back and seeing that you got that wrong, it has to sting a little. I mean, I don't know. I think so. A thick conducting slab, surface charge, blah, blah, blah. So here we have gravity against the electric force. Since it's a conducting slab, we have all of the flux above the slab, right? Because the flux is 0 inside the conductor. Remember that? Electric field 0 inside conductor, that's important. Would that be on the final? I would expect there's stuff about knowing the electric field inside a conductor is 0 and working out consequences of that logically. Yeah, that should happen. All right, anyway, that one. Us physics instructors, we love Gauss's law. We love it so much. It's kind of embarrassing. So, is it an idol for us? I mean, probably the case could be made. Let's see here. So this is your one of the variants of the, suppose you've got a charge and there's a cube and you're asking how much flux is passing through what? Oh, I give you the flux through the top face is 125, and I say how much charge is in the box. I tell you that the charge is at the center of the box so that there'll be a symmetry. That putting the charge at the center of the box means the flux through any of the faces is the same. And since there's 6 faces and you know the flux through one face, you can cipher that the total flux is 6 times that. And then that, by Gauss's law, is the charge enclosed divided by epsilon naught, which allows us to calculate the charge. This down here is just a straight, this is the formula for the Coulomb field for an electric. You know, if we have a charge at a position and we ask for what the field is at this field point xyz, then we do the displacement from the field point to the source point, x minus L, y minus 2L, z minus 3L, and this is the reason I have distance cubed down here is because I didn't put a unit vector over here, right? So you've got options. You can either put r hat over r squared, or you could, as I like to put, r over r cubed, just because it makes the formula less annoying to write out. Oh man. I guess I'm going to be sick over break. This is wonderful. Anyway, so my children have been coughing for a week. It finally got to me. What's this one? Oh, I can't read it back here. So here you got 2 charges, here and here, and you know their values, and you know that the length is 50 centimeters. Basically, the point here is to calculate the electric field at that point. So you got to calculate the electric field from that's, you know, this is a negative charge, so it goes towards that one. This is a positive charge, so it goes away from that one. And the distance in both cases is L squared, where L is 50 centimeters, 0.5 meters if you like. And so I calculate the sum of the electric fields because that's how we can go. Superposition gives us the net electric field. And you get that. And of course the magnitude is the square root of the sum of the squares. And the angle, you got to think about. This one here is in quadrant 2, which means I can't just use inverse tangent. I need to think about it. And I think about it, I get 123.7. So yes, standard angle, it does matter. The force, it goes in the opposite direction here because I put a negative charge there. So the negative charge turns the electric fields, the force due to the electric field the other way. And instead of having 123, you're going the opposite way. Instead of 123, you're down here at like minus 56.3, or if you like 303.7. So, yeah. The electric field points the direction in which, if we put a positive test charge there, the electric force would go, right? Electric field's pointing in the direction in which we would push a positive electric field due to the source charge's presence. If there's a negative charge, then the electric field will pull that negative charge, the force that it produces, in the opposite direction. All right, I'm going to stop talking. This is the very long line charge problem. I think this is just, yeah, this is just a plain old very long line charge. Calculate the, magnitude of the electric field, the distance r from it. So you look at a cylinder, length L. Inside that cylinder, lambda L would be the charge enclosed, and the flux will just be radially outward. So 2 pi RL E gives me the flux through the cylinder, the Gaussian cylinder. There's zero flux through the caps, so we kind of ignore those. And lo and behold, we get E is lambda over 2 pi epsilon r radially outward. That's the... Now, of course, there's other versions of this which are interesting, right? Like, what if instead of a line-like wire, you have like a cylinder wire where the charge is smeared out? Then you have to look at a Gaussian cylinder both outside and inside the charged wire, right? And you get two cases. We worked an example like that in class, and maybe in your homework too, right? Here's the analog of that for the sphere. Here we have a spherical charge through a shell from A to B. And so again, the game is, well, you had to pay attention to which case you're asked about. This one, I only asked about the electric field inside where the charge is. So I need to figure out how much charge is enclosed inside the Gaussian dotted sphere there. So to do that, I take the charge density, which is this, and I multiply by the volume enclosed, which is that. All right. 4/3 pi r cubed minus a cubed is the volume of the spherical shell that's enclosing charge there. And then the other thing with this one is there's also an extra charge at the origin, so I have to lump that in. That just adds. So the charge enclosed is the charge at the origin plus the charge on this, out here, this part, which is why I got this, which then we can solve for E is that, right? Now after test 1, we could also ask a similar question, which is, what's the voltage, right? What would the voltage be? And add on to this question. You wanted to find the voltage for this situation, you would set E equal to minus dVdr and integrate. So if I was to set this to minus dVdr, I could integrate, I would find the formula for the voltage in this situation, the potential per unit charge. That was not asked here. Why? At this point, we had no potential, right? This is before test 2. Here's a charged rod variable density problem. To find the electric field over here, we have to integrate the electric field because it's variable. The little bit of electric field we get from that little bit of charge is this much, and it varies as we go from here to, along the thing. We're different distances from the source point to the field point. So we have to do an integration, and we do that, and that gets us to that electric field. This kind of problem, so as you're thinking about the final exam, like a lot of it, when you're dealing with all the problems at once, part of the game, what's new to the final that wasn't present in test 1 is the possibility to use different techniques, right? Like, we have Gauss's law, we also have the theory of potentials. So like this one, maybe you could now do this using voltage, to solve it. You know, that might be an interesting exercise for you to try to figure out what's the voltage function due to this line segment of charge, right? Add up the potential there. But be careful. Be careful with applying Gauss's law where it doesn't apply. You know, your problem has to have the necessary symmetry to use the kind of arguments that we've done, because we don't know calculus 3, so we can't actually do surface integrals for really ugly stuff. Anyway, I think this one was similar to like a problem in class, wasn't it? I think I solved this or something like it in class, I'm pretty sure. I might have solved the uniform charge in class, right? Here you got charged positive, so I charge in here, I got charge, a conducting sphere out here, right, a shell. So we know the electric field's 0 inside the conductor. That kind of like forces certain things. If the electric field is 0 inside the conductor, and I have some kind of net charge on the interior sphere, it must then be the case that there's negative of that charge on the edge, on the interior edge here, right? Otherwise, you'd have charge enclosed for the Gaussian sphere, which is inside the conductor, which would imply the electric field's non-zero by the spherical symmetry. But that's not the case. So it must be that there's a net, like you have to have the charge distributions conspire so that you induce charge on the edges of the conductor such that such that the electric field inside the conductor is 0. In the static electric case, right? More recently we've been looking at currents. In the case that there's current, there can be an electric field inside the conductor. It pushes the electrons along and such, right? But we weren't there at this point. If you guys have a question, feel free to jump in. You're going to ask me how long is the final, how many questions, what should I expect, is studying the old tests helpful? Yes, I don't know, maybe. What?
Will you have the test 3? I was like, last time I checked it, what the key wasn't on Canvas. Will you have that like submitted sometime?
Well, I mean, I meant to put it on Canvas. If something's missing, let me know.
Okay.
You know, you tell me now, so I'll try to remember. But if I don't remember, email me. Yep. I'm not trying to hide those from you guys. It's just I forgot, you know. Ooh, this problem. This was bonus, huh? Well, anyway, yeah. That one was neat, I think. I'm not sure I'm awake enough. Well, that's not the right thing to say. I'm not well enough to look at this problem. Let's... test 2. We found out about potential per unit charge, right? So I give you the voltage, you calculate the gradient, you put a minus on it, that's the electric field. So, you know, I'm personally of the opinion that problem 1 is free points. These are free points for you to take. If I give you this question on the final, please take this gift which I freely offer. Do not refuse it. You know, you can do this. Everybody can do this. You just have to partial differentiate these, and don't forget the minus, and yeah. Now this one here, find the energy needed to assemble the triangle of charge. So like, I need, you know, it costs you nothing to put the first one in place, right? It costs you this much energy to bring the second one in place. It costs you that much energy to bring the third one in place. Well, also this, because by the time you get to the third one, you have to contend with the first and the second. Excuse me. This problem is easier than previous versions of this problem I have asked. So just something to think about. Do be sure in this kind of problem you're actually thinking through the geometry of how far apart the charges are, right? Because if I change this problem to calculate the work done to assemble a square of charge, okay, you know, 4 charges on a square, all of a sudden then you've got to be careful because certain charges are distant side length apart, certain charges are diagonal distance apart, and that matters. This glosses over that. So I regretted giving it to you guys in some sense after I did, because I'm like, oh man, So I have not learned who understands the geometry and who's kind of So in some sense this problem is too easy. But anyway, what's done is done. So what's this one? Spherical shell, voltage 0. So here I told you the voltage 0 at the origin. Find the voltage as a function of distance r. So basically here, what I do is I use Gauss's law to find the electric field, and then I integrate the electric field and put a minus on it in order to find the voltage. Because in this case, the electric field is just a function of r, so that means the voltage is minus dV dr. And as such, we can integrate. And the thing with this one, though, is you got to be careful. I have given you the constraint that the voltage is 0 at the origin, right? Which means that you have to add a constant in order to make it such. So it leads me to the formulas that I have down here. The details don't so much matter as the principle of the thing, which is when you integrate, you add a constant, right? Now that constant can be 0, but if people put conditions on you, like the voltage has to be 0 at the origin, then that forces the constant not to be 0. Actually, it forces it to be something else. It turns out it forces it to be 3 alpha r squared over 2 for this problem. And with that, you can double check. I mean, you can check it out. If you put in r equal to, oh goodness, I'm sorry, I'm not at the origin in this case. This is not the origin. Obviously, this formula doesn't work at the origin, right? Division by 0, not a good look. Well, anyway, I talked about this before. If you go back, you can find me talking about these solutions in the problem session, I think. 42. Another 42. What a coincidence. So, yes, you do need to know how to find equivalent capacitance, equivalent resistance. Hopefully those aren't too mysterious. What's the general principle for capacitance and resistance? It's like if it's been connected for a very long time, the capacitors are what? Like open circuits, right? Essentially and you can just assume the current through the capacitor is 0, which means essentially this just reduces to these 3 resistors in series, and you can kind of answer the question going from there. I think everybody needs to study these a little bit more carefully than you have. Like everybody lost points on these somewhere. Yeah.
Good question. Why is VC at 0? Because it's on a straight line to ground.
Because because VC is between these capacitors, which are charged, and a charged capacitor has voltage.
Oh, so like with a control wall path, it's not just a straight line, it's still has.
Straight line. What do you mean?
Oh, I thought like there was a rule that like if the capacitor is connected for like a long time to the point where it's fully charged up to alright, then it's practically like a straight line.
Well, no. It's the opposite of a straight line. It's an open circuit.
Oh yeah.
But more to the point, like when the capacitor is very charged, fully charged, that means there's voltage across it, right? Essentially, almost by definition. But well, where the definition stops and the physics starts, I don't know. But
Thank you.
Good question. What I'm trying to say is, don't ignore that problem in your studying, because like a lot of people lost points there. Those points you can get back on the final, I think it's possible. This one here is pretty plain Jane, like 10 volts, 30 ohms, they're connected, so Ohm's law tells me the current through there is whatever it is, 10 volts divided by 30 ohms, 0.33 amps. And then on the other hand, over here, I've got 5 volts here, I got 10 volts here. That means there has to be 5 volts across this. So 5 volts divided by 20 ohms is 0.25 amps. Now I found a way to make it more complicated, but you could also reason like I just did. All right. I mean, you would not have found me writing this down when I was in community college. I would not have done this. I would have been embarrassed to write that equation. Are you kidding me? Like, you just look at it. 10 volts here, 5 volts here. That means there's got to be 5 volts here, because the sum of this voltage plus that voltage has to match that one, But you can also draw the loop equation. Kirchhoff's voltage law gives you this, and you could solve for the 0.25 amps. Yowzers. We talked about these. I don't want to talk about it right now, but should there be a problem like this in the final? Yeah, there really should be. Should you make sure you have a way to do the algebra here to double check yourself? You really should. So like even my little silly little calculator has a way to do systems of equations on it, you know? So it would be wise if you haven't figured out already how to solve a system of equations with this thing, because you can, right? But anyway, I guess it's kind of late in the game to tell you that, but it's still true. And if you haven't taken, have you taken circuits yet? Yeah, are you allowed to use a calculator in there?
Yeah, circuits. Yes.
Like use MATLAB? You guys ever like solve equations by hand?
Yeah.
Yeah.
Kramer's rule and
Kramer's rule and
we were interested in building a matrix. We set up a matrix
Ah.
equation and then solve that.
so you just like symbolically?
Yeah.
Okay. Is Math 221 a prerequisite for that class?
No.
Why not? Why isn't this class a prerequisite for that?
Because
Whatever. I know. Reasons. I guess you got to go on, right? Yeah. Life is short. Where was I? So you set up the Kirchhoff's voltage laws. You sum the currents. Current in equals current out, right? And you solve. These do take time to get good at, though. I do get partial credit, though. So there's that. So we have worked out the calculus of the RC circuit, how to charge, right? So you should review that, make sure you can do these. We also have studied the RL circuit, right? I think this problem is a lot easier than it might have seemed at first glance if you go back and look at it. Problem 10 is. Energy does matter, so make sure you study problem 11, like the work energy theorem, right? The work is the change in kinetic energy. But if the net force is electric, then the change in kinetic energy is also minus the change in potential energy, but minus the potential energy is also Q times the change in voltage, right? Because potential is potential energy per unit charge. So Q times the change in voltage gives me the change in potential energy with respect to the electric force, and so that's how you were supposed to think through this. A lot of people got that wrong. That is usually something that I test on. Where else am I? So we're test 3, which I have not posted yet, I guess. So, well, I guess we're out of time. So, you know, guys, it's been a good semester. I think there's hope for many people in here to survive, even to thrive. So we shall see. Thanks, guys. Oh, before I forget, you guys will probably end up taking the final at the time when it's scheduled, right? But I'll make an announcement sometime soon. These are I believe, the 5 times I'm giving a final. 3 of them are on Monday, 8, 1, 3:30. I've got one on Tuesday from 3:30 to 5:30, and I've got one on Wednesday from 3:30 to 5:30. So like these are the times that you might be able to find me to give me something or talk to me. Or if you don't, for whatever reason, want to take the final at this time, and you really, really would rather take it, you know, Wednesday at this time, talk to me, all right? So I can be a little bit flexible with like when you take the final, if it's helpful to you. But you do got to ask me about it, okay? Thanks, guys.